Okay, this is 8.2, inverse relations and functions. Okay, are we ready for this? All right, here we have our title slide. Okay, sorry. All right, moving on. All right, graph on the same coordinate plane. So we're going to look at these two graphs side by side. G of x equals 2 times x minus 1. Well, remember, when we graphed these square roots, we want x minus 1. Why is it not? To equal 0, 1, 4, and 9. For that to happen, x is going to have to be 1, 2, 5, and 10. Okay, so that's my x value. The y value would then be the square root of each of the x minus 1 values times 2. So the y value is going to be 0, 2, 4, and 3 times 2 is 6. So I have 1, 0. Nope, wrong. Okay, 1, 0 is right here. And then 2, 2. And 4, 5, 2, 3, 4. 5 is all the way up here. Okay, I can't plot the rest of them, but basically it's that. All right, minus 2x squared plus 1. This is a parabola. The minus 2 means it's opening downwards. The x squared means it's a parabola. Sorry, plus 1 means it's up here. Accidentally flipped. There we go. My vertex is up here at a plus 1 on the y-axis. It's going to curve downwards. So if I plug in 1 for x, I get 1 squared is 1. So that's a minus 2 plus 1 is a minus 1. So I'm all the way down here. Remember, I have symmetry, so I can do this. So basically, I look something like that for h of x. So this is h of x, and this is g of x. My vertex, I'm sorry. Okay, next page. All right, the inverse of a function may or may not be a function. Okay, let me show you a real quick little sketch of an example over here. A parabola, its inverse would be this. The inverse is not a function. The original parabola is. I'm using the vertical line test. Okay, so its inverse is not a function. A parabola's inverse. Okay, so the inverse of a function may or may not be a function. In example 1, q is a function, but q inverse is not a function. When a relation or function is expressed as an equation in x and y, a rule for its inverse can be found using, this is my method, SSS. The first S is for substitute, where you change the f of x to y. Now, sometimes it's given to you where y already is there, so then you just skip that step. It's already done for you. Next, we switch x and y. Notice that the y became an x and the x became a y. Now we just solve for y. SSS, substitute, switch, solve. So I solved for y by subtracting the 6. I get x minus 6, and then I'm going to divide by 3, and that's going to give me x minus 6 over 3. And that's what y is equal. So this is now the inverse relation of that equation. Okay. Moving on down to the next slide. Find the rule for the inverse of 2x plus 4. Well, first step, substitute. So this is my first S. F of x became y. Now I switch. Second S. Notice x and y are switched. I now have x equals 2y plus 4. Third S, solve for y. So I subtracted the 4, and now I divide by 2. And I end up with x minus 4 over 2. Okay, so this is going to give me 1/2 x. By putting the 2 underneath both terms, it's like the reverse of common denominator. I have x over 2 minus 4 over 2, right? Which is going to give me 1/2 x minus 2. Okay, now find the inverse of x squared minus 2. All right, substitute. It's putting the y in. Switch. I switched my x and my y values. And now I solve for y. So I'm going to add the 2 to the other side. But now I have y squared. So I have to square root both sides because I have to get y. So the only way to do that is to get this out of the square root. Remember, when I do that, I have to have a plus or minus. Okay, so now that's my answer for y equal. Now, generally speaking, if that's a function, we square roots have to only use the plus, can't use the minus. But this would be our equation. Because we said the inverse of a parabola is not a function. All right. So these are the two rules of the inverses of this function. These two functions. All right. There we go. Now here are the graphs of two lines. The blue and the red are inverses. Okay, now the way we know that is I have their rotations across the x equal y line. This dotted is x equals y. And these are rotated around that x equal y, which gives me the inverse function. So what I can do is if I take this point here on this graph, and I have a perpendicular to the x equal y line, I get the inverse number. So notice this is -1, 2 over here. Over here, it becomes 2, -1, the inverse. X and y are switched. Same with this one. This one's giving me inverses. Right? Here it's -1, 1, and on the other side, it's 1, -1. Inverses. That's what the graphs look like, just so you know. All right, the horizontal line test. Now, we talked about the vertical line test before. The vertical line test was that if I can draw a vertical line through more than one point anywhere along the line, it's not a function. Okay? Here, I'll kind of show you what I'm talking about. So, that would be a function because I cannot draw a vertical line anywhere and have it cross in more than one spot. On the other hand, that would not be. See, I just drew a line and hit 3 places at one time. Not a function. Well, we now have the horizontal line test going the other direction. And what that tells me is whether the inverse is a function. So as we said, with parabolas, it doesn't pass the horizontal line test, so its inverse is not a function. And sure enough, if I draw the inverse, you can see it is not a function using the vertical line test. So the horizontal line test only tells me about the inverse, not about the function or equation that I'm dealing with. That may or may not be a function. But if it passes the horizontal line test, then its inverse is a function. All right, any function whose inverse is also a function is said to be one-to-one. You have one x for every different y, and every y has only one x. It goes both directions. If a relation and its inverse are functions, then we know that the composition, remember that circle thingy is the composition of the function both directions, the inverse inside the function and the function inside the inverse, will always give you x. Both of them have to give you x. That's how we can check for inverse functions. That's a check for inverse. Okay, now we're back to our cute little function boxes. We had those yesterday. All right, if I put a 10 in, here out comes 24. I put a 10 on this side, out comes 3. Now, for the blue box to be an inverse of, my blue box is an inverse of the orange box, then if I put the 3 in, out comes 10. 10 in, 10 out. Okay, so when I compose these, whatever goes in is what comes out. That's our test. Same over here. 10 goes in, 24 comes out. Put that into the inverse, and out comes 10 again. So these are matching each time. I'm sorry, I think I forgot there was a note. Yeah, there we go. All right, so show that these are inverses. We do that by composing them. So first, I'm going to put h of x inside g of x. That's what I have here. What that means is I have g of h of x. Well, g is 4x minus 1, so I have 4 times whatever's in the parentheses minus 1. What's in the parentheses is my x plus 1 over 4. All right, now the 4s, when I multiply these two together, the two 4s cross out, leaving me with just x plus 1. And then I have a minus 1. So plus and minus 1, they cancel each other out, and I have just x. Passed step 1, but it has to pass the other as well. It won't always. So now I look at h of g of x. So that becomes h of g. Let me do it in a different color. G of x is 4x minus 1, so it goes here. H of x was x plus 1 over 4, so I plug this in for x, 4x minus 1 plus 1. Notice the minus 1 and the plus 1 disappear. So now I have 4x over 4. The 4's cross out. I have just x. So since I have just x in both compositions, this is indeed an inverse. So the answer to this would be, if you will, a yes. Did I miss it again? No. Okay, good. Oops. All right. So inverse functions have a one-to-one relationship. For every element in the domain, there is a unique element in the range. And for every element in the range, there's a unique element in the domain. Okay. Let me see if I can explain this. Okay, remember I was just showing you with the parabola. Its inverse is not a function. So it does not have this one-to-one relationship. Yes, every x has only one y value. Okay, but every y has two values, 1, 2. Do it with blue. 1, 2. Okay, to be an inverse, a one-to-one function, the y values can't have any matching. Okay. That's what that is saying. 5a. Given h of x, which is the square root of x minus 3, find the rule for the inverse. Okay, substitute, switch, and solve. Substitute. I have y instead of h of x. Switch. I'm switching my x and my y's. Solve. I solve for y. So I square both sides. That's how I got the x squared. Right? And then now I have to add 3 to both sides, and I get x squared plus 3 is equal to y. Now I have to find the domain and range for both functions. So first off, the very first function, that's this one, remember the graph would look like this. Well, actually, it should be at a positive 3. So it's going to look, okay. My shapes aren't great. It's going to be at positive 3, and it's more like that. Okay, but that means my domain is greater than or equal to 3. It also means my range is greater than or equal to 0. There we go. Now, the inverse is rotated across the x, the y-axis, and I end up with something along the lines of this. And this is now a positive 3. So my role reversals have changed. Notice that the range of the inverse is equal to the domain of the original function. And the range of the original is equal to the domain of the inverse. Because they switch. That happens when you do that switch. The middle S. Okay. So now if you graph both, I did a rough sketch, but this is what you would get right here. Okay, this is actually easy to graph. You find yourself a couple of points and then you flip them for the inverse. So for example, for h of x, I want x minus 3 to equal 0, 1, and 4. So therefore, x has to be 3, 4, and 7. So what that's going to give me for y is 0, 1, and 2. So what I do is I graph 3, 0. Here, I'm going to change because I've got... Okay, I hope you can see this. Right here, 3, 0, 4, 1, and 7, 2. 7, 2. There we go. Okay, now the inverse plots them the other direction. So for my inverse, I plot 0, 3. Instead of 3, 0, 0, 3. There we go. And 1, 4 instead of 4, 1. So 1, 4. And then also 2, 7. So 2, and this is all the way up at 7. There we go. So it's actually really easy. You plot one, and then you merely flip all the coordinates of the graph points you plotted. All right. And we're done. We're down to our homework. All righty.